Swayam Prabha. Digital India. Educated India.
In the last class, we looked at the experiment 2D NOESY, that is nuclear Overhauser effect spectroscopy, and how it is useful in determining structures of molecules, and we also saw some practical matters related to this experiment, such as how the intensity varies with distance and the mixing time, how it should be chosen. One problem with 2D NOESY is that it does not work for many molecules in a particular size range. And what do we do in such cases? If NOESY cannot be used, how can we determine the structures of those molecules? So, there is an alternative experiment which we can use, and that is what we are going to see in this class, and that is known as ROSY. So, as you can see in this slide, the 2D ROSY means it is rotating frame NOESY. So, the word is just the word rotating frame is there, and rotating frame Overhauser effect spectroscopy. So, this is an alternative to 2D NOESY experiment, and so let us see how this works and why is it required. So, in this experiment, so if you recollect the previous class, we looked at how the NOESY experiment is done. That is done by applying 3 pulses. So, what one was 90-degree pulse, then we had T1 evolution, then we applied one more 90-degree pulse, brought the magnetization to minus Z, and then during the mixing period it was allowed to interact with the another spin, and after this transfer the second spin was detected by applying one more 90-degree pulse, and then it evolved. So, in this experiment ROSY we do it in a different manner. So, here what we do is we apply a 90-degree pulse, then allow the spin A to evolve, that is the same approach what we saw in the case of TOXI. Then you mix the magnetization by applying what is called as a spin lock. So, this is nothing but a weak irradiation applied for a duration of this time 200 to 500 milliseconds. And after that, during this period, again similar to what happens in NOESY, the magnetization from one spin is transferred, or polarization from one spin is transferred to the second spin, which carries with it the information of the chemical shift during T1. So, the second spin, when it is now comes to the xy plane, remember here if you look carefully, we have started from x axis pulse. So, the magnetization is in the y direction here, and it remains y throughout. There is no need for another pulse to bring the magnetization to y. So, in NMR, remember we always apply 190-degree pulse to bring a magnetization from z axis to y axis. But if the magnetization is already along x or y, we do not need to do anything, we just need to directly start detecting that signal by using that detector, and that is called FID. So, we do not detect here, we just allow the spins to evolve in chemical shift, and they start moving according to the chemical shift frequency, and when the intensity at any point here is modulated, means connected or related to the chemical shift frequency value, and that intensity is transferred to the next spin based on its because of the spin lock here, and that is because of the through space interaction, and after that interaction is over, then the second spin now which has got the energy or magnetization from the first spin starts moving, and that is gives a second spin chemical shift. So, that 2 spins are connected to each other, correlated by this manner. So, now question is, if you look again, if you recall, this is exactly the same as a TOXI spectrum, TOXI pulse sequence. So, the question is what was different here, why is it similar to a TOXI? The reason is, yes, it is very similar to TOXI, in fact it is like a TOXI itself, but the only difference is the power levels are slightly lower than a TOXI, and the time duration is very long compared to TOXI. In a TOXI we use typically around 60 to 80 milliseconds, and this is about 3-4 times bigger, longer, it can go all the way up to 500 milliseconds. So, that is the difference as far as NOESY and TOXI is concerned, but the picture, the pulse program like this sequence looks exactly same. So, now question is, why are we doing this ROSY experiment at all? Why does not the NOESY help always? So, what happens is, there is the theory which we will not go into detail in this course, but the theory says that suppose by accidentally your molecule is such that the product, the multiplication of omega into tau c. What is omega? Omega comes from your spectrometer frequency, and tau c is the rotational correlation time of the molecule, and if you recollect, we saw in the previous classes that it is related to molecular weight divided by 2 in kilodaltons, and the value is typically in nanoseconds. So, this product, if it happens to be close to 1, then the NOE effect, it goes to 0. That means, even if the atoms are close in space, you will not get any cross peak between them, because there is no way that they can transfer to each other, and the reason is the transfer efficiency has become 0 because of this spurious or strange phenomenon, which is well explained in theory. Of course, it is not that strange, but it is interesting that at this point you will get a 0. So, typically this will happen if your molecular weight, let us say, is 1000, the molecule which you are analyzing, and if you are working at this frequency 400 megahertz. Okay. So, at that frequency omega is how much, is 2 into pi, 2 pi into frequency. So, just not directly frequency here, you have to use the 2 pi and multiply with the tau c for this, and if you recollect the math, the tau c for this is going to be 0.5 nanoseconds. So, 0.5 nanoseconds into 2 into pi into 400, if you calculate at room temperature. So, remember, this is a very important point, because temperature matters here. We saw that earlier, that if tau c temperature goes up, the tau c changes, and temperature goes down, the tau c will change. So, based on this at temperature, you will see that for this particular case you may get around 1.2, and that means the efficiency of NOESY for this molecule at that frequency at that temperature is not very good. So, if you are forced to work at under those conditions, those spectrometer and that molecule, you will have to try an alternative experiment, and that is why we use ROSY. So, ROSY is, the information wise, is very similar or same as NOESY, which means that similar to NOESY, the intensity of the cross peaks is proportional or inversely proportional to the r to the power 6, where r is the distance between two atoms. So, similar to what we do in NOESY, we choose a mixing time and we look at the intensity, we measure or calculate the intensity of the cross peaks from the spectrum, and based on that we calculate the distance. So, for example, 1000, if you say, one more thing, if you look at it, a typical amino acid residue in a protein, an amino acid is typically, we say, the average is 100 or 110. So, that means this will correspond to a 9 amino acid protein peptide. So, if your peptide is 9-10 amino acids, and if you are working at 400 megahertz at room temperature, then it is highly likely that you will not get a good NOESY, or maybe nothing at all. So, therefore, you should use this experiment. So, that means if how will the spectrum look if the NOESY effect is 0? So, if you think about it, so imagine that in the experiment which we saw in the last class, we expect a transfer of polarization from spin A to spin B, but if spin A does not transfer completely to B, what we saw is we get what is called as diagonal peak. A diagonal peak is a peak which comes because of incomplete magnetization transfer. So, therefore, if you have a 0 transfer, nothing is transferred. So, all the peaks will be in the diagonal, because nothing is transferred to anything else. So, therefore, in your NOESY spectrum, if you see at just only a diagonal peak and you do not see any cross peak, it means that your problem is because of this particular reason. Okay. So, therefore, one should now concentrate, look at either change the magnetic field, or that means I should go to, let us say, 600 megahertz if I have in my laboratory, or you change the temperature, because remember, temperature also will help you to come out of this condition. By changing the temperature will affect the tau c, or you must basically look at some other molecular weight. So, this is the way why ROSI is important, because it overcomes all this problem and you do not have to worry about NOSI and directly record a ROSI spectrum. Now, in a ROSI spectrum, the spin exchange means the polarization transfer takes place during the period known as spin lock period. See, this word spin lock period is coming because of this. There is a isotropic mixing, that is what we saw in Toxi. So, during this period there is a transfer going on. So, therefore, remember, if you recollect, I just now as we discussed, Toxi experiment is also exactly same as ROSI. So, therefore, one has to optimize spin lock so that you do not start seeing Toxi peaks or artifacts or Toxi type of problems in NOSI. So, these are practical aspects which are important to know, because Toxi and ROSI have same pulse program. So, whatever, but remember, as I said, in Toxi we of course use very short mixing time, whereas in ROSI is little longer. So, this is an experimental spectrum, how it looks. So, you can see here that there is a cross peaks, and you can see there is a diagonal peak and there is this cross peaks. So, red color. So, you see one thing, if you notice immediately, the cross peaks are opposite in sign compared to diagonal and chemical exchange. So, what is chemical exchange? We will worry about it little later when we come to the advanced NMR topics. We will cover chemical exchange, but what is currently we have to worry about is this peak, the diagonal. So, you see the diagonal is black in color, that means it is, let us say, positive, and the red is opposite to diagonal peak, means opposite in color, because it is negative. So, the cross peak and diagonal peak have a negative phase relationship between each other, and that is why we say that it is very nice, because you can immediately figure out any peak which is opposite to diagonal is the actual cross peak which we need to worry about. There is another very beneficial or useful feature in ROSI which is not present in NOSI, is as follows, that remember we discussed what is called as spin diffusion peak. A spin diffusion peak arises because two spins A and B are not closer than or farther than 6 angstroms or 7 angstroms, that means they could be 10 angstroms, but still I may end up seeing a cross peak in a spectrum between A and B, which is not correct. I do not expect A and B to show a cross peak, but it is showing a cross peak. If you look at it in other way, if a person does not know the structure that it should be 5 or 10 Armstrong or so, the person may think that A and B are now close to 5 to 6 or less than 5 to 6 Armstrongs, because I am seeing a peak in the NOSI spectrum. So, this will lead to a wrong structure because in reality they are about 8 Armstrongs, but in practice using my equations and using my the idea that intensity is proportional to power 6 1 by r power 6, I may end up interpreting that these two peaks, these two atoms are less than 5 to 6 Armstrongs. Okay. So, this is a misinterpretation and can very much lead to a wrong structure. So, why did it happen? This happened because A and B were not close in space, but there was a third spin, suppose we call it as A prime or C, which connected A and B, because first that magnetization went from A to C and from C to B during the long mixing time. So, if the mixing time is not chosen appropriately, I may end up with this kind of artifacts or this kind of problem. So, in a NOSI there is no way that a given peak we can say whether it is a direct NOSI peak because of less than 6 Armstrong distance or it is coming because of spin diffusion. Very difficult to say, unless of course the one option we use is to vary the mixing time. So, let us say you record your spectrum at different mixing times. So, if you record a spectrum at different mixing times, remember we saw that the intensity is proportional to the mixing time. It increases with mixing time to some extent. So, therefore, if the intensity of a cross peak keeps on increasing as I vary the mixing time, then that particular peak I can say is coming from direct NOSI effect. But if the intensity of peak does not vary with mixing time, it decreases, then I will say it is an indirect NOSI effect, that is spin diffusion peak. So, for a spin diffusion peak, the intensity does not increase proportionately with mixing time. That is one way in NOESY to rule out whether a peak is coming because of direct NOESY or through spin diffusion. But the disadvantage now is that you need to record several 2-dimensional NOESY spectrum with different mixing time, and remember each 2D spectrum takes about hours to record, a few hours, and therefore, if you want to do several 2D experiments, you may end up spending days, 1 day or 2 days just for this purpose. But in case of ROSY, what happens is that ROSY, your red color which is shown here is red color is a direct cross peak and this is diagonal peak. So, if you have a spin diffusion peak, then that will come as black color, which will be the same as the diagonal. So, interestingly, the diffusion peak will now can be distinguished from the direct cross peak, because there will be a change in the sign or change in the color of the peak. So, based on that, one can now distinguish and say confidently that look, this is a spin diffusion peak and something else, and some other peak is a actual cross peak. So, therefore, we can focus, we can then when we analyze or interpret the intensities, one can then ignore those black peaks and focus only on the red peaks. So, this is one way to look at spin diffusion, but of course, there is another thing in ROSY is that exchange peak, that and also in NOESY, an exchange peak happens also in NOESY. So, NOESY and NOESY both show a very interesting feature, which is a very important dynamics information in many systems in chemistry. We will look at it as I said in the advanced section, but let us ignore. So, keep in mind that in ROSY, the spin diffusion peaks, that is multi-step NOESY peaks, are opposite compared to direct one step NOESY peak, and therefore, it is very easy to distinguish. But then the question you may ask is, why do not we then do ROSY every time? Why do we ever have to do NOESY? The reason is because of this factor here. If you see this diagram picture here, the magnetization is in the y axis here, x or y, and then it remains in x or y for a long duration up to 500 milliseconds, and then you detect. So, during this portion of the time, it decreases because of T2 relaxation. So, remember T2 relaxation is all happens in the xy plane, and T1 relaxation happens in the z axis when magnetization is going to the z axis. So, T2 relaxation starts playing a big role in this case. So, if my T2 is short, which is typically the case for larger molecules, if you let us say a peptide which is 15 amino acids or 20 amino acids, as you go increase the number of amino acids, or if you look at larger molecules, the T2 effect, T2 is very short. So, by the time you apply this isotropic mixing, that is what is called spin lock or a weak RF radiation, the spin starts relaxing towards z axis very quickly. So, therefore, the signal intensity when you reach here is very less. So, the overall sensitivity of ROSY is less compared to NOESY. So, only if there is no option for NOESY, ROSY is resorted to, means people use ROSY if in case you are not able to get a good NOESY, but otherwise NOESY is still preferred, because as far as I control my mixing time properly, the spin diffusion is not such a big problem. So, from one, if you are experienced, then you will know what mixing time one should use, and therefore, you do not have to worry about this negative positive, and you can analyze a NOESY which is more sensitive compared to ROSY. So, this is things end to the ROSY part, that is the ROSY and NOESY. We will look at one last 2-dimensional experiment before we move on to the heteronuclear. So, we will look at one more homonuclear experiment, 2D homonuclear, which is known as inadequate, again a very interesting acronym, and that stands for this particular word, which is incredible natural abundance double quantum transition experiment. So, now the name sounds very complicated, but actually the experiment is a very simple experiment. What it means is, it is what it tries to do is, it tries to correlate like any other 2D the chemical shift of carbon to carbon. Okay. So, remember our focus is now carbon to carbon, we have come out of hydrogen. So, this is typically a carbon carbon correlation experiment and used very frequently in chemistry, not so much in biological molecules, because the sensitivity is of course very low. So, here what are we trying to do? We are trying to correlate or connect two carbon atoms. So, let us see how this happens. So, this I said is a very useful for establishing carbon carbon correlation, that means two like cozy. Remember in a cozy we saw proton to proton correlation. Similarly, here we try to do carbon to carbon correlation again using J coupling. So, J coupling is a common feature everywhere, only through J coupling we can transfer polarization if you want to study like a cozy experiment. So, it is very useful for natural products and so on, but remember it is C13 detected, means everything is carbon 13 here, there is no hydrogen involved, proton involved. So, the carbon 13 is not a very sensitive nucleus, because it is natural abundance is very low, number 1 100 times less compared to proton, number 2 it is 4 times less gyromagnetic ratio, it has 4 times smaller gyromagnetic ratio compared to proton. So, these two factors really reduce the sensitivity of carbon if you are studying at natural abundance. So, therefore, this is a very insensitive experiment, it requires very long time to record and more sample. Remember one of those slides we saw long back in the theory part, where we saw first part which was more of theory, we saw that the sensitivity of NMR is proportional to square root of measurement time and directly proportional to concentration. So, if the sensitivity is very less like this, you either need long time or you need more sample, or you can use both, take longer time with more sample. So, this is one class of experiments which falls under that. So, let us see how this works. So, this is basically as it says here, how what information do you get from inadequate? Inadequate looks at pairs of doublet cross peaks along the horizontal axis, which means that two corresponding carbons are directly connected. So, let us say example, suppose this is a carbon atom, this is what is shown here on this x axis here, these lines are lines are nothing but peaks of a carbon spectrum. So, remember if you recollect, we saw that carbon spectrum looks like single sharp lines because we decouple the hydrogen. So, there is no J coupling to hydrogen which can be seen in a carbon's 1D spectrum, plus carbon spectrum do not have any carbon carbon interaction. So, there is no homonuclear J coupling, because neighboring two carbons, the very low probability that both of them will be C13. We saw that it is 1% of 1%. So, therefore, in a carbon spectrum you will typically see single lines. This is not a real spectrum here, but in a reality you will not get very much different from this. So, let us say I have recorded a sample hypothetical, we will see a real example in the next slide, but let us say that we have a molecule which has spectrum like this, a carbon spectrum. What I am trying to do now is look at the next connected carbon atom, that means neighboring carbon atom. So, let us say, let me draw this example. So, let us say I have something like this going on in the molecule. So, I have 1, 2, 3, 4, 5. So, what is this inadequate experiment doing is trying to connect the neighboring carbons, or trying to tell you which peak here this carbon is connected, this carbon is connected to which other carbon. So, for example, let us say this particular carbon may be this particular peak, then this particular carbon will become this peak here. So, basically we are trying to form a connection between two neighboring carbon atoms. Okay. So, this is what is shown here. So, let us say we start from 1, some arbitrary peak, you are using the word double quantum here. So, let us not worry about what is double quantum for the time being, this is more mathematical or That's why we won't be able to cover this in this course, but for us what matters is just the appearance of peaks. So, you have a carbon peak which is, let us say, position 1. Remember this both axes, okay, both side, this horizontal vertical axis and horizontal is carbon to carbon. So, both dimensions are carbon. So, but the only thing is in this axis we do not get direct carbon chemical shifts, we say that it is a combination of two chemical shifts. Okay. So, what happens is it is basically a chemical shift here is the chemical shift of 1, some peak 1 plus the chemical shift of its connected peak. So, both these peaks are connected to each other. So, both the chemical shifts you add them together, sum of the chemical shift is what you will observe here. Okay. So, let us say this is directly connected to peak number 2. So, it will be in the same line. Okay. So, then what you do next is you go vertical in this line. Okay. So, this is basically, if you go vertical, this position will be 2 plus 3, 2 plus 3 means chemical shift of 2, this 2 plus chemical shift of the next peak 3. So, that is what comes at this position. So, if you go in the horizontal line, it is 2 plus 3 is this peak, and this will be 3 plus 2. So, both are equal. So, they are in the same line. So, 3 plus 2 comes here, but 3 plus 4 comes in the vertical, because I have to add, this is 3 and I have to add a chemical shift 4. So, there will be addition to that, it will come here, and then again 3 plus 4 and 4 plus 3 is same. Then comes 4 plus 5. So, 4 plus 5 is comes down. Why does it come down? It comes down because 5 is on this side and 3 was on that side. So, whenever you go to downfield, depends, it can either increase or decrease, or it is always opposite. So, whatever happens to this chemical shift here is more than this chemical shift, or I can reverse the approach, I can say this side is less and this side is more, it does not matter. What matters is that when you go this side, it is on one direction and this side is opposite direction. So, from 4, when I take this peak to 5, it is coming down, because the chemical shift of 4 plus 5 is less compared to chemical shift of 3 plus 4. So, 4 plus 5 comes here, and if you go horizontal, this is 5 plus 4. So, 5 plus 4, 4 plus 5 is same, but now 5 is connected to 6. So, this 5 is connected to 6. So, 5 plus 6 is different now, it goes up, and this is 6 plus 5. So, 6 plus 5 and 5 plus 6 are same. Then the 6 is connected to 7, then you go up and see the same line, the next peak, and then go horizontal, that is the last peak 7. Okay. So, basically what is happening here is we are going from horizontal vertical, horizontal vertical. So, when you go on the horizontal line from one atom, one peak to another peak, we get the neighboring connection information. So, we get two atoms connected to each other directly through one bond. Then we go up, we get second connection, we go left, we get another connection. Like that we can walk like this and keep connecting two neighboring carbon atoms, and this vertical will match with these peaks here. So, you have to place your carbon 1D spectrum on the top, and then along this line you start looking at those chemical shifts. So, this corresponds to this corresponds to this, and so on. Okay. So, let us look at a real concrete example. In this case menthol is shown. So, menthol has this structure here, you see on this side, okay, and then you can see that these are the numbers we have put on the carbon atoms. So, let us say you start from 1, so this assignment which carbon is which chemical shift has already been known in this molecule. So, therefore, this is just an example. So, suppose you have 1 here, atom number 1. Remember, atom number 1 is directly connected to 2, it is also connected to 6. Okay. So, but let us follow one path now, let us go from 1 to 2, then 2 next is here. Now, 2 is connected to both 3 as well as 7. So, you see there are 2 peaks here, 2 is connected to 3, and we will see later how it is connected to 7. So, first let us see its connection to 3, which has come here. Then from 3, if you go vertical, it is 3 again, because it is the same line as 3, but now if you go horizontal, you get 4. Then you go again vertical along 4 to remain on 4, but next horizontal gives 5. Then you go along vertical to get 5, and then gives you 10. Remember 5 to 10. So, we have completed one path. So, along 10 you do not see any vertical, if you see carefully along 10 I do not see any other peak. So, therefore, 10 is the last atom. So, it is stops there. Okay. So, it is like a train moving from one station to another station and it stops at the last station. Now, this was one pathway, means one direction. Now, I can also go via 1 to 6 to 5 to 10. So, let us start from there. So, this is from 2. Okay. So, let us look from 2 onwards. So, 2 from 7, 7 to 9 and 7 should also to 8. So, if you see here we started from this 2, there are 2 peaks. Earlier we looked at 2 to 3 connection, now I am looking at 2 to 7 connection, then 7 to 7 vertically up, then it will branch out into 2 possibilities, one is 7 to 9 and other is 7 to 8, that is what we see here. So, 7 to 9 connection, and so essentially we are connecting all the peaks which are each next to each other, direct one bond. So, this is complete this side. Now, we are still left with 1 to 6 this pathway which we did not see. So, that what comes here. So, we start from 1 again, remember 1 we had 2 peaks, one was this pathway, other is now this pathway 1 to 6, then 6 we go vertically up, you get this peak which is again 6 only because we are in the line of 6, but then if you go horizontal here it is a connection from 6 to 5, 6 to 5, and then now I expect 5 to 10. So, first I will go vertically on 5 and see wherever 5 is there. So, I can see that there is 5 here and then sorry we will see a 5 here from here to here and then 5 to 10. So, 5 to 10 pathway is common. So, this 5 to this 5 to this 10 is same and this 5 to this 5 to this 10 is same. So, because 5 10 is finally a single connection, whether you come like this or you come from other side, there is no distinction. So, this is how this inadequate experiment works. Again, if it's we will look at the application of this later on in a real system where we will use this to calculate or we will use this to get the connection information. So, we will now this brings actually to the end of all 2D experiments that we have looked at, and we will just quickly summarize. So, what we looked at is homonuclear 2D experiments. So, we saw that the simplest experiment is 2D cozy, which helps us to get information between 2 protons which are directly J coupled to each other. Usually that is coupling is either 2 bonds or 3 bonds, and in literature in textbooks you will see many variants of 2D cozy. The very important covariant is called 2D DQF cozy, double quantum filtered, which is exactly same or same information as cozy, but is much better than cozy. So, normally nowadays people do not do 2D cozy as such, they do what is called DQF cozy. Information wise they are same, but the problem is 2D DQF cozy is not sensitive, it is less sensitive. This is similar to like rosy and nosy which we saw, depending on the sensitivity you can choose. TOXY is a very important experiment, we saw that it gives all the information about a spin system which is very useful. The spin system was we saw is a network of coupled spin, means which are coupled to each at least one neighboring spin. And for structure determination we saw the important experiment of 2D nosy, where all protons which come close in space within 5 to 6 angstroms will show chemical shift correlation. And interestingly, as I said, just a mere presence of a cross peak between 2 atoms tells us that they are less than 6 angstroms. So, just a presence is enough to give some distance information. And then we saw that in the case of nosy does not work many times depending on your molecule and spectrometer frequency, and in such cases we have to use rosy. So, this brings us to the end of 2D homonuclear NMR experiments. Now, we will move on to heteronuclear 2D experiments, that is where we see chemical shift correlation between carbon and proton, and then that will be in the next week, and when we will see how these two homonuclear and heteronuclear together can be combined to get a complete structure determination of molecules.